Hi, my name is Chris Hegarty. I work in the Java Platform Group at Oracle, and today I'm going to be talking about the road to the Java 11 HTTP client. In this session, we're going to be answering three questions. Why are we adding a new HTTP client? How long does it take, and what does the road of development look like? And what are the benefits that you, as an application developer, can get from the new HTTP client in Java 11? Enhancements to JDK are done through JDK Enhancement Proposals, JEPs. JEP 110 is one of the first public documents on the HTTP client, and it is useful to look at the motivation section in this JEP. It contains a number of points discussing the URL connection API, which is the current API for performing HTTP exchanges. URL connection was added in JDK 1.0 back in 1996 and is protocol agnostic. It supports multiple protocols like FTP, Mail2, File Access, at one point Gopher, as well as HTTP. URL connection in fact predates HTTP 1.1. Looking at the HTTP timeline, we can see that the RFC for HTTP 1.0 was published in 1996, 1.1 in 1999, and more recently HTTP 2 in 2015. There have been countless bug fixes in the HTTP protocol implementation and numerous enhancements such as larger than 2 GB content lengths and the expect 100 continue header, to name but a few. The implementation has reached its limit for complexity after being around for more than 20 years. Given that URL connection is protocol agnostic, then it can be a little cumbersome to use for HTTP, since it suffers from restrictions of being a common protocol API. While there is a concrete HTTP URL connection subtype, in many cases there still just isn't any natural place to document some of the HTTP specific behavior. URL connection is based on Java I/O streams, which are inherently blocking. This may not have been such a limitation back in 1996, but it is today. Threads are a valuable and costly resource, and we don't want to unnecessarily tie them up, especially waiting for data to be received from the network. Looking again at the HTTP timeline, the HTTP 2 RFC was published in May 2015. The application semantics of HTTP 2 are mainly the same as that of HTTP 1.1. All the core concepts, such as requests, responses, HTTP methods, status codes, URI, and headers, are mainly the same. Instead, HTTP 2 modifies how the data is formatted and transported between the client and server. HTTP 2 does, however, bring some new concepts that would have been very difficult or almost impossible to model in the URL connection API, like server push, which we'll take a look at later. The HTTP 2 implementation is very different from that of HTTP 1.1. Defining a new HTTP client API for the Java SE platform is not easy, especially if you expect it to be around for the next 20 years. JEP 110 was created in May 2014, almost exactly 1 year before the HTTP 2 RFC was published. Work actually began well before this date. In fact, some of the early prototypes that went through several iterations were done around the Java 7 timeframe in an open source project on the now defunct java.net site, which is still available in the archives. So this project has been worked on by several engineers and spans over a number of years. JEP 110 was integrated in JDK 9, and JDK 9 shipped in September 2017. As you will know, Java 9 brought a large language change in the form of the module system, and the Java runtime image is comprised of a set of modules. Alongside the module system, a new concept of incubating features was added. We'll take a deeper look at incubating features in a moment, but for now, all we need to know is that the HTTP client was added in JDK 9 as an incubating feature. A new incubator module named JDK Incubator HTTP client was added. That module exports a single package, JDK Incubator HTTP, that contains the complete HTTP API. JEP11 is an informational JEP that describes what incubating features are, their purpose, and their delivery mechanism through incubator modules. Simply put, incubator modules are a means of putting non-final APIs in the hands of developers, while the APIs progress towards finalization or removal in a future release. Incubating an API is desirable as it allows the standardization of an API to be deferred for a short period of time. The API is still part of the JDK download, so is available to the large number of Java developers. The incubation time allows for these developers to provide feedback on the API, as well as the ability for the API to incorporate this feedback before it is standardized. An incubating API is expected to be relatively short-lived. In all cases, it will be removed in a future release, either because it is standardized, in which case its module and package name will change, or if some fatal design flaw is discovered, then it will be dropped. Looking at the HTTP client class from JDK 9 or JDK 10, you will see that its module and package name clearly identified as being incubating. There is also a more scary looking warning that the API is an incubating feature, and as such will be removed in a future release. All this helps to notify the developer that if they are using this API, then they will need to take some action when updating it to a future JDK release. Incubator modules are not resolved at compile time, so an additional command line option needs to be specified to tell the compiler to add the incubator module and make its types available. Here we are making the HTTP client module available, so the add modules command line option is specified with the name of the HTTP client incubator module. Similarly, incubator modules are not resolved at runtime, so the add modules command line option is needed again with the same value, the name of the HTTP client incubator module. Alternatively, a modular application can include an explicit requires directive in its module info source file, naming the HTTP client incubator module. Regardless of how incubator modules are resolved, either through explicit requires directives in the module info source file or through command line options, a warning is emitted at both compile time and runtime to indicate that an incubating feature is being used. The warning includes the name of the particular incubating modules that are in use. In this case, just the incubating HTTP client module is being used. Again, this warning is intended to help notify the developer that an incubating feature is in use and that an action will need to be taken when updating to a future release. So that's what we did in JDK 9. In JDK 10, the implementation was completely overhauled to improve reliability and to make it more robust. The API was also updated to incorporate the feedback that was received on the incubating JDK 9 version. For Java 11, a new JDK enhancement proposal was filed, JEP 321, to standardize the API. This required giving the HTTP client a standard module and package name, JavaNet HTTP. This standard package now includes the complete API, and the incubating version has been completely removed. Any code that runs on JDK 9 or JDK 10 and uses the incubating API will need to be updated. At the very minimum, the import statements will need to be changed to reflect the new package name, and also any module info source files that contain requires directives naming the HTTP client incubator module will now need to use the new standard module name. Similarly, any command line options specifying the incubating module name will need to be updated, or may even not be necessary, since all standard modules that are part of the Java SE platform are resolved by default when running an application from the class path. Let's take a look at how to do that. Okay, so here we have a utility get method. It retrieves a given URI and returns the response body as a string. First, it creates a new HTTP client over which the request will be sent. Then it builds a new request with the given URI. Then the send async method is invoked to send the request, and the body handler as string factory method returns a body handler that converts the response body bytes to a string. The send async method returns a HTTP response of string. That can be then chained up with the then apply method from completable future to map the HTTP responsive string to its body type, which is string in our case, and a completable future of string is returned. The main method simply calls get with the given URI and then join to block until the completable future completes. Then the response body is printed out. This is using the incubating version of the API from JDK 9. So let's run that. We can see the warning that an incubating module has been used and the name of the module. And then the program executes and prints out the response body as a string, which is just some XML. There's also a modular version of the same code. Its module info requires the JDK incubator HTTP client module and exports a single package P that contains the code. The code is almost identical to the previous code, only it prints out a modular test so we know that this code is actually executing. So let's run that configuration. Again, we have a warning from the compiler and from the runtime that the incubating HTTP client is being used, and again the response body is printed out. So let's update this code for JDK 11. First thing we do is we can update the STK being used by the IDE, and now we have a lot of errors because the incubating API is no longer present in JDK 11. So let's update the import statements to reflect the new standard package name, which is javanet HTTP. We can still see that there's red lines, and this is because the require statement is not right. So let's update the module name there first. Okay, our import statements seem to be accepted now. Oops. Now the factory methods have been renamed in JDK 11. They are all prefixed with of, and they've moved to the body handlers class. So body handlers of string. So let's run that now and see what happens. Okay, we've got an error at compile time because the JDK incubator HTTP client module is not found. My IDE is being configured in its preferences to add the incubator module as a command line option. So let's remove that. We no longer need that. And run the modular application again. Okay, great, it works. This application only uses the HTTP module, so it only needs to require javanet HTTP. It could, of course, have required Java SE, which gives you the full Java SE platform. And again, that runs and prints out the response body. So let's update the non-modular application as well in the same way. And again, the factory methods have been moved and renamed. So let's run the configuration for the non-modular application. There's an application running on the class path. And it again mentions the fact that the incubator module is not found. So we need to edit the configuration of this, edit the configuration and remove the explicit add modules that was used as a runtime argument when we were using JDK9. So let's run that again. And it works, it prints out the response body. So we've seen how to update a modular and non-modular application, to update the import statements to reflect the new package name in JDK11, as well as the new module name in the module info, as well as some other minor changes around the renaming and moving of some of the factory methods. There are a number of benefits that application developers can get from using the new HTTP client, and we'll take a look at the most significant of these over the next number of slides. Here are some of the goals that are listed in JEP 110. Support for HTTP2, of course, as well as HTTP 1.1. Provide an asynchronous API, so as to get away from the blocking semantics of the existing URL connection. Use more modern language features like generics and Lambda, as well as more modern platform APIs like Completable Future and the Reactive Streams interfaces. Additionally, there is support for the handling of the WebSocket upgrade and a low-level WebSocket API. As I said earlier, the application semantics of HTTP2 are similar to that of HTTP 1.1. There are, however, significant differences in how the two protocol versions operate. HTTP2 uses just a single connection between the client and server, which reduces the overhead of setting up new connections, especially for HTTPS, where the TLS handshake can take some time to complete. This single connection between the client and server can have multiple HTTP requests multiplexed on it at the same time. HTTP2 provides a new mechanism called server push, where a server, upon receipt of a request, can, if it determines appropriate, issue synthetic requests to the client for resources that it believes the client will likely need along with the original request. This can be used to speed up the retrieval of resources with a large number of embedded links. The on-wire format has been updated significantly from that of HTTP 1.1. HTTP2 uses a more compact binary format, and headers are compressed using HPACK compression. The HTTP client supports both HTTP 1.1 and HTTP 2, but prefers HTTP 2 by default. For new, clear, non-TLS connections, the client automatically adds the appropriate protocol upgrade headers to let the server know that the client supports HTTP 2. If the server also supports HTTP 2, then it can reply as appropriate and the connection will be upgraded. For HTTP over TLS, the client uses the Application Layer Protocol Negotiation TLS extension to try to negotiate H2 with the server. If the server supports H2, then H2 is used. In all cases, if the server does not support HTTP2, then the connection falls back to HTTP 1.1. As of JDK11, the TLS 1.3 protocol is supported. The HTTP client leverages this and attempts to negotiate TLS 1.3 for all new TLS connections. The HTTP client supports an asynchronous mode of operation. Requests sent with the sendAsync method return a completable future of HTTP response. Completable future provides a number of methods for building chains of dependent actions that can be run either synchronously or asynchronously. In this example, sendAsync is given the request to be sent and also a body handler that converts the response body bytes to a string. The completable future then apply method maps the HTTP response to its body type, which in this case is a string. The then accept method consumes the string and just prints it out. Finally, the join method blocks until the response string is printed. The HTTP client follows the familiar builder pattern. There are factories for creating builders for both the top-level HTTP client and the HTTP request types. In this example, the HTTP client new builder static factory method returns a new builder of HTTP clients. A connect timeout for new connections is set to 20 seconds and the client is built. The HTTP request has a similar new builder factory. Then the request URI is set, a request specific timeout, a header indicating the content type, since this will be a post request. The body publishers of file factory method is used to return a request body publisher that publishes the content of the given file path. The request is then sent. The Java platform provides support for reactive streams through a number of interfaces in the Java Util Concurrent Flow class. There is a publisher for producing items, a subscriber for consuming items. A subscriber subscribes to a publisher and can issue a request for items as needed. This request mechanism provides the subscriber with back pressure, since it is in control of the maximum number of items that may be sent to it. As we've just seen in the last slide, HTTP request body is provided through a body publisher. Body publisher is a subtype of flow publisher that publishes HTTP request body as bytes. The HTTP request body publishers class provides a collection of factory methods for creating publishers for most common use cases. For example, publishing request body from a string, or publishing request body from a file, and more besides. Similarly, on the receiving side, the HTTP response body subscriber is a subtype of Java Util Concurrent Flow subscriber. It is a subscriber of response body bytes. Again, there is a class body subscribers that provides a number of factory methods for creating body subscribers for most common use cases. For example, converting the response body bytes into a string or streaming the bytes to a file. Custom publishers and subscribers can be written by implementing the body publisher and body subscriber interfaces. To summarize, the standard HTTP client added in Java 11 is a replacement for performing HTTP access through the URL connection API, which, as we've seen, is now more than 20 years old. The HTTP client API was incubated in JDK 9, refreshed in JDK 10, and finally standardized in Java 11. Code using the incubating version of the API will need to be updated for Java 11. Minimally, the import statements will need to reflect the new standard package name. The HTTP client API uses more modern language features like generics and Lambda, as well as more modern platform APIs like completable future and the reactive streams interfaces. You can download Java 11 now at this URL. Please join us at OpenJDK or follow us on Twitter at OpenJDK or hashtag Java 11. My own Twitter handle is @Chegar999. Oracle is the steward of Java, providing a large amount of development engineering funding for the Java SE platform and OpenJDK. Oracle provides leading-class premier support for a low cost that's easy to purchase with simple pricing tiers. Thank you for watching.